Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And this is the last in a series of lectures on the precise definition of a finite limit at a finite point. However, you can see on the screen right now, we're actually growing that definition to be the precise definition of an infinite limit at a finite point. So we have our function approaching infinity now, or negative infinity. And this expanded definition to start working with infinities is actually a little bit easier than the epsilon delta or finite limit at a finite point definition. So let's start with just reading out the definition quickly here. Definition of an infinite limit at a finite point. Let f be a function defined on a delta neighborhood centered at x equals a. So I'm going to go ahead, as I read this out, I am going to go ahead and showcase kind of what this is saying. So we have a function that's defined on some neighborhood, delta neighborhood, centered at a. Remember, all neighborhoods, in calculus at least, do not include their centers. They're punctured open neighborhoods. So we have a function defined on this highlighted neighborhood here, trying to get somewhat precise there. And again, looking back up, then the limit as x approaches a of f of x is said to be infinity, means that for every, well, you know what? You can kind of just visualize with me that this really is saying you have some value of, you have x equals a, some vertical asymptote. And your function, as x gets really close to a, starts skyrocketing. Okay. And it could be, but from either side. So we'll just go ahead and say from either side it's skyrocketing. Because you could do this with single-sided limits as well. Okay. But for right now, let's just deal with this idea that from both sides it's approaching infinity. So the limit as x is approaching a of f of x is infinite, as you can see there. The blue curve is approaching infinity, means that for any m that somebody hands us, notice that this m is not an epsilon. In the epsilon delta proofs, that was an epsilon. For every epsilon somebody hands me. Well, here's the deal about an epsilon neighborhood. An epsilon neighborhood is a finite neighborhood, or a smallish neighborhood around a finite point. So as you can see right here, for an example, you have an x or a value of 2. So you have a delta neighborhood around 2. And that delta neighborhood right now is of size 0.62. And as x gets really close to 2, well, we can capture our function in an epsilon window, right? That function itself is captured in that little epsilon window, which is the red highlighted region there. However, suppose that instead of the function 2 raised to the x, we were dealing with something like 1 over the quantity x minus 2 raised to the second power. Now, if you look at this, there's no epsilon neighborhood that I can create around, let's say, a height of 4 here. There's no epsilon neighborhood that would contain this black curve. That black curve would jump right outside of it. In fact, no matter where you park the y value, let's say we tried it at 16, a height of 16, the function would go well above your epsilon neighborhood if you had a little wiggle above and below a height of 16. It would shoot outside of that. So we are not concerned about epsilon neighborhoods here when you have something going to infinity. Instead, you're willing to say, listen, I want, for an example, I want a y value that you need to get beyond. So somebody comes in the room and they say, I bet you can't build a delta neighborhood so that all the x values within that delta neighborhood lead to y values above this height, right? And we can do that. We could totally do that. So all I need to do is just tighten up this neighborhood tight enough. And now this app was not designed for this, but the reality is if you tighten up that delta neighborhood tight enough, you'll notice that your curve is above that height of 16 for all x values in that neighborhood. And that's kind of the idea of this definition. In fact, that's not just kind of the idea, that is the idea of the definition, is that we are challenged with tightening up this delta neighborhood so that when somebody comes in and says, hey, this is a height of m, you want all your x values to land on your curve above that height of m. So you need to tighten up this delta neighborhood to get a smaller delta neighborhood about a, so that when you have x values within that delta neighborhood, and I'm just going to artificially tighten up this delta neighborhood here. When you have x values within that delta neighborhood, they strike the curve above the challenged height. And that is the difference between the epsilon delta proof and the infinite limit proof at a finite point. So limit as x approaches a of f of x is equal to infinity means somebody's going to walk in the room and say a billion. I bet you can't make the y values greater than a billion. Well, maybe you can. Create a small enough delta neighborhood about your center, and you might be able to get the y values, the function values, above that height of a billion that they've challenged you with. So for every huge number, and that's what this, by the way, greater than means, it just means this is a huge number. Hugely positive, actually, number. And so for every hugely positive number, there is some small number, delta, such that as long as x is within a delta neighborhood, and sorry, my screen is doing that, it's because because of the fires in California right now, the Wi-Fi is just messy. Anyway, such that if x is within a delta neighborhood of a, then our function can be made to go above that height. A similar definition holds if you say, well, my function actually is not going to positive infinity, but instead my function is going to negative infinity. So let me draw that situation. Let's suppose that you have a function that at x equals a, call this x equals a, you have some function that just dives down to negative infinity on both sides. Well, then somebody's not going to challenge you with an epsilon neighborhood, because that would be silly to say, oh, here's a height of 7. Let's make a little neighborhood here and see if you can capture your function in there. You won't be able to. Your function's going to fall below that height very quickly. So instead, somebody's going to come in here and say, I bet you can't get below some massive value. And I think I still call that m in my version of this. No, I guess not. I call it n. So there you go. So somebody gives you a massively negative number that you have to get below. You have to get your function below that massively negative number. So hugely negative is what I'll put there. So somebody's going to challenge you with a hugely negative number if your function is supposedly going to negative infinity. And your job is to find a delta neighborhood about x equals a so that all x values within that delta neighborhood land on your function well below that height. And that's really what this definition is saying, is you can find a delta such that as long as x is close to a within a delta neighborhood of a, then your function will be below the height they challenged you with. Now, to illustrate this idea, we're going to actually just take our time, just like we did with the precise definition of a finite limit at a finite point. We're going to take our time building this. It won't take too long, honestly, but just a little bit of time. And if you can see in my lecture notes here, at the top, this is page 22 out of 22 right there. I was supposed to be an arrow. It's not. So anyway, page 22 out of 22. So this is the very final example out of this. So there's not much to build here, but the idea is this. we have some function, in this case, 1 over x minus 4 being squared. Now, if you were to graph that, you guys know, you're in calculus, you know that that is the graph of 1 over x squared shifted to the right 1, 2, 3, 4 units. I should probably zoom in because this is just terrible that I'm doing that, right? So I'm going to zoom in here, and this is 1 over x squared graph, but shifted to the right 4 units. You can easily see that as x approaches 4, the function launches off to positive infinity. And so somebody's not going to come in here and say, hey, listen, I bet you the limit as x approaches 4 is going to be infinity, and then challenge you with an epsilon neighborhood. Instead, they're going to say, well, I want you to prove that this is launching off to infinity. And you say, I could totally do that. And they say, great. Well, then if that's the case, and if you're super confident about that, I'm going to give you a height that you have to get above of some massive number. And so your job, again, is to build a delta neighborhood centered at 4 such that all the x values in that delta neighborhood launch up and above onto the function above that height of whatever massive number they hand you. So let's go ahead and investigate that. How close to x, I'm sorry, not to x, how close must x be to 4? I always say that backwards, by the way. To ensure that the function is greater than 1,000. So really what this is saying is somebody challenged you with a height of 1,000 here. And we just want to know, well, how close do we have to actually be to the value of 4? Well, that's not a terrible idea or a concept to kind of deal with. Let's go ahead and transform this sentence here into mathematics. And we'll do that using the fact that we know the distance between x and 4 is called the absolute value of x minus 4. So we want the absolute value of x minus 4 to be really small. That's really what we want. And to get that distance to be really small, because again, how close does x have to be to 4? That's just saying x is within a delta neighborhood of 4. We need to find that delta. So that, and here's the one equation they've handed us, or inequality in this case, so that 1 over x minus 4 quantity squared is greater than 1,000. I can work with that. I want to get the absolute value of x minus 4. That seems to be pretty easy to do here. Let me grab this and move this off to the side. If I have 1 over the quantity of x minus 4 and quantity squared, and I'm told I need to get this above a height of 1,000, well, I could take the reciprocal of both sides. By the way, you should know that if you take the reciprocal of both sides of an inequality, the inequality sign switches. Try it out. Just create any two numbers you want. Positive numbers, please. Create any two numbers you want, like 3 and 7. I hope everybody agrees 3 is less than 7. Well, what about 1/3 compared to 1/7? And I hope you also all agree that 1/3 is greater than 1/7. So it is just with that small justification, it seems to be true that when you take reciprocals, the inequality signs will switch. Okay, that being said, I've just taken the reciprocal, not taken the reciprocal of both sides. Now what I'm going to do is go ahead and take the square root of both sides. So this implies, via taking the square root, that x minus 4 is going to be less than the square root of 1 over 1,000. Now, obviously, square root of 1 is 1. Square root of 1,000 is not what you would think it would be. It's 10 root 10, unless you thought it was going to be 10 root 10. Then it's exactly what you think it should be. Now, remember what we want. We want the absolute value of x minus 4 to be less than some number. Well, this is a little bit of a hand waviness here. If I just tell you that, oh, we're going to throw on some absolute values. So I do need to remind you of something from your algebra course. from algebra, maybe I'll write this down below so that we have this, but from algebra, the square root of some number squared is going to always be the absolute value of that number. Try it out. Think about square root of 3 being squared. Well, 3 squared is 9, square root of 9 is 3. Okay, I guess you could say that's the absolute value of 3. Fine, I'll agree with that. But what if I said the square root of negative 3 squared? Well, negative 3, you square it, it becomes a positive 9. Take its square root, it becomes 3. Which, by the way, is the absolute value of negative 3. So that's a really strong justification for that theorem from algebra. This is actually a theorem from your algebra course. That being said, when we took the square root of both sides here, I did a little bit of no-knowing by not putting the absolute values here, because I took the square root of a square. There you go. Now we have the inequality we want. How close does x have to be to 4 so that 1 over x minus 4 quantity squared is greater than 1,000? Well, that's a simple answer now. This close. Whatever that number is, it's that close, right? So x has to be within 0.032 units of 4. That's a rounded version of 1 over 10 times the square root of 10. So it's incredibly rounded version. Well, now let's zoom back out. That idea right there, how close, sorry, I have to wait for my screen to catch up to me. How close does x have to be to 4 to ensure that this is true, is actually how the proof goes. So let's do the same work. How about 20,000? How close does x have to be to 4 so that we can guarantee that this function right here is greater than 20,000? So what's the size of our delta neighborhood to guarantee that all those x values lead to function values above a height of 20,000? I'll just erase that and put in 20,000 this time. Well, the idea is still the same. We want to find out how close x has to be to 4 so that our function right there is greater than, and let me erase this, greater than 20,000. Well, that's still asking the same question, right? I want the reciprocal, which is x minus 4 quantity squared, to be less than 1 over 20,000. And that would mean that I want to take the square root of both sides, the absolute value of x minus 4, to be less than 1 over the square root of 20,000. I just took the square root of both sides. And because I know I'm going to be grabbing a calculator, I will just go ahead and leave that in that form. And right now, all I'm doing is typing this into a calculator, and I get the following. X has to be within, and let me erase that, 0.1270, and I'll just round to the same number of significant figures, roughly within 0.00707 units of 4. All right, so that's not too terrible, really, if you think about it. So how does this lead us to the idea of the actual proof? And again, I apologize for my screen. It is just the reality of Wi-Fi. So now somebody comes in and they say, prove to me then. I mean, you've already shown me that you can get above 1,000, you can get this function above 20,000, but I really want to know that you can prove to me that as x approaches 4, that function will tend to infinity. And now the epsilon gauntlet, which is technically we don't have an epsilon, but a gauntlet has been thrown. We will assume that somebody's handed us a massively large y value. So I'm going to write down, just like we would with any epsilon delta proof, I'm going to write down that somebody's handed me some massive number. And when I say massive, I mean much greater than 0. And I'm going to say then there must exist some delta neighborhood such that as long as our x values are within that delta neighborhood of a, that should imply that our function is above the challenged height that they told us we couldn't get beyond. And so just like with epsilon delta proofs, I'll go ahead and do some scratch work off to the side. Now, I hope you don't mind my terrible screen, first of all, and also I'm going to just erase this because I don't want that in my way. And I'm going to zoom in here and just write scratch, and hopefully my screen doesn't go too haywire. All right, scratch right here. And let's go ahead and assume where we want to end. Just like any epsilon delta proof, you assume where you want to end in your scratch work. So we're going to assume that our function is already above that challenged height of m. I'll write that down over under our scratch work. This is what we're not showing the world. So we're just going to assume that our function is already above that challenged height of m. And we want the distance between x and a to be less than delta. We want to find a delta neighborhood, basically, is what I'm saying. Well, the function that we're working with is 1 over the quantity x minus 4 and quantity squared. Again, we're assuming that we've gotten that function above that challenged height. And we want the distance between x and 4 to be less than some given number delta. All right. So let's see, how am I going to get the absolute value of x minus 4? We've done it so many times that you might have forgotten, but let's just do it again. Take the reciprocal of our assumed state. We've assumed that our function is greater than m. Let's take the reciprocal of both sides. And that will show us that the x minus 4 quantity squared is now less than 1 over m. And we'll take the square root of both sides. Remember, the square root of a square is an absolute value. Less than 1 over the square root of m. Notice all of our answers before were 1 over the square root of 1,000, 1 over square root of 20,000. So this kind of makes sense. So now I know, right? Absolute value of x minus 4, I wanted to get that. I got it. So that piece right there must actually be my delta. And now I can start my proof. All of these infinite limits at finite points, all these proofs are a lot easier than the finite limit at a finite point. They tend to be much faster. That's why a single example is really all I need here. So let's go ahead and start our proof. And I'll refer to the scratch every once in a while. And I'm going to do my lawyer speak just because I want to, and because I think when you hear somebody say something, like with a constant pattern, then as you do proofs, you start hearing that in your head and you start kind of developing your logic that way, right? So if I constantly argue like a lawyer and through all these proofs, then every time you do a proof, you're going to be like, well, ladies and gentlemen of the jury, and you're going to kind of lay out your arguments the same way. So here we go. Somebody says, hey, I hear there's a claim that the limit as x approaches 4 of 1 over the quantity x minus 4 squared is infinity. But we don't believe that. And you say, it's my job to you to prove that. And they say, I don't believe you at all. You say, okay, well, I'll go with that. I tell you what, you give me any number and I can guarantee I can get that function above it. And they mull it over and they say, well, you know what? I don't want to actually give you a number. Just assume I've given you a number, a huge number. You say, okay, I'll do that. I'll assume that you've given me a huge number. So for any huge number m, there you are. Are you happy I've assumed that? And they say, yeah, I'm super happy you've assumed that. You've kept it very general. And I say, you're right. That's my job. But you know what I'm going to do? For any super large m that you're going to give me, I will assume, or I will let, I don't want to use the word assume in a proof. I will let delta, the size of my delta neighborhood, equal 1 over the square root of m. I say, I really don't understand why you would do that. And you don't have to draw the picture, but maybe there's somebody slow in the audience and you're like, listen, you have this a value and I'm just creating this little delta neighborhood around a. And I'm telling you, all of those function values or all those x values will lead to function values. I promise you that are going to be above the height you've challenged me with. And they say, I don't believe you. And you say, I don't care, because I'm still going to prove it. So for any massive number you hand me, I'm going to let delta equal 1 over the square root of m. And they all kind of scoff at you. And you say, well, just bear with me, if you will. If it's the case that the distance between x and 4, which is what we are approaching, is less than delta, and somebody stands up and they say, what do you mean by that? And you say, I'm just saying, if x is super close to 4, like within our delta neighborhood, this little delta neighborhood over here. So then they sit back down. They say, okay, I'll go along with that. You say, ladies and gentlemen, if x is within a delta neighborhood of 4, then I hope you all can agree, because of my choice for delta, the distance between x and 4 must therefore be less than 1 over the square root of m. Everybody nods their head at that. They're okay with that. And you say, well, I hope you don't mind. I'm just going to square both sides. So squaring the left-hand side, there's no longer a need for an absolute value, because the square will automatically force it to be positive, right? So there's no real need for an absolute value. And everybody still nods to that. Oh, yeah. When you square a number, it becomes positive. Great. And on the right-hand side, if I square 1, it's 1. If I square the square root, it just becomes m. They say, okay, great. And you say, ladies and gentlemen, I'm really going to astound you here. I'm going to take the reciprocal of both sides. Again, all I'm really doing is climbing this ladder of my scratch work, okay? You say, ladies and gentlemen, I'm going to take the reciprocal of both sides. That's 1 over x minus 4 quantity squared. Of course, you know from algebra, when you take the reciprocal of both sides of an inequality, your algebra teacher told you that the inequality sign will switch. And they say, yes, I had a really good algebra teacher. That person was awesome. And you say, as well, they should be. And you get to that. And you say, well, those are the reciprocals, and I've swapped the inequality sign. So is everybody happy? And they say, yes. And you say, then I'm done. And they say, why are you done? And you say, because I've just shown you that the function is now above the height you've challenged me with. Because the function was 1 over x minus 4 quantity squared. And they say, well, wait, now I don't believe you. What if I give you a height of 3 trillion? And you say, well, then delta is just equal to 1 over the square root of 3 trillion. This proof still works. It works for any height you hand me. So, in your face. QED, the Latin in your face, quod erat demonstratum. That is how a proof for an infinite limit at a finite point works. They're actually very nice. The questions I'll often get here, I think through all the years, generally speaking, people don't have a ton of questions on this, other than there might be questions like, well, what if it's only going to infinity on one side? And if that's the case, if somebody comes in and says, well, I don't have the limit as x approaches 4 of the 1 over the quantity x minus 4 squared equals infinity. Instead, I have something like, I'm going to actually put it right here. I have something like the limit as x approaches 4 from the, let's go from the top side of 4 there, of 1 over x minus 4. And that's actually equal to infinity. And you say, well, that's fine. Just prove it using a one-sided limit. You're just above the height of 4. That's your entire proof's basically the same. You're just on one side of 4 there. So there's going to be a point within your proof where you don't have to worry about the absolute value. That's all. It's not that big of a deal. And then somebody else will say, what if it was negative infinity? Well, not much changes. You can create actually pretty much any function you want that dives down to negative infinity. In fact, you know what I'm going to do here? I'm going to create an example. I'm going to say, what about the limit as x approaches, let's go to 5 from the left-hand side of 1 over x minus 5. That is actually, I'm claiming to you, it's going to be negative infinity. Now, you don't have to believe me. I'm going to prove it. So, to prove it to you, I need to recall the definition of an infinite limit at a finite point. And that definition is just that for any given hugely negative number, because it's going to negative infinity. They're not going to hand me a height of 20,000 here, because why would they? They want to see that this thing's going to negative infinity, so they're going to give me a height of negative 20,000, right? So there's no point in saying n is positive. N, the number they're handing me, is going to be super duper negative. My job is still to find a delta such that if the distance between x and a is less than delta, that should imply my function. Now think about this graphically. They're telling me my function's diving down on the left side of 5, right? X equals 5. They're telling me my function's diving down. Well, then obviously they're challenging me with a level, a height of n. They're saying, I bet you can't get below this. So my end result should be my function is actually below that height. Now let's see if we need any modifications to this because it's a single-sided limit. I'm going to tell you, no, we don't. Right now, we don't. We're going to use a little bit of logic to make modifications, but honestly, we don't need a ton of modifications to that, even though we're dealing with a single-sided limit here. Let me erase all this, get it out of my way. So my scratch work goes like this. I'm going to go ahead and assume, again, my scratch work, I can write the word assume down. That's perfectly fine. So I'm going to assume that my function is already below the height of n that they challenged me with. And I want sort of the distance between my x value and a to be less than delta. And notice I said sort of because there's something interesting about this. So remember, our x is approaching 5. So we want that in absolute value to be less than some magic number delta. Now the caveat with one-sided limits that you have to be somewhat careful of is you have to remember the true definition of the absolute value. Now, for those who are not in my class, people on YouTube, in the world of the internets and interwebs, you probably have not seen my version, or if you have, then good for you, but you may not have seen my version of the absolute value. It's the true version of the absolute value, but it's incredibly important that you know it for calculus. The absolute value of something, well, if that something was already positive or non-negative, there's no need to have the absolute values. You could just say, well, great, that's just some positive or non-negative thing. However, if that object was actually negative, then you need the opposite of that happy face, the opposite of that object. Because if it's negative, the absolute value is going to force it to be positive by throwing a negative in front of it. A negative times negative is now positive. And here's where one-sided limits you have to be very, very careful of. And this stands for the previous lecture as well. I didn't really talk about it, but it is true. If you're dealing with a one-sided limit, it is sometimes the case, not always, but it's sometimes the case where you really need to consider, what is x minus 5? Is that positive or is that negative? And if you have x approaching 5, in this case from the left, and that's exactly what we're dealing with. Let me zoom over. There we go. If you have x approaching, that looks terrible, right? If you have x approaching 5 from the left, that means x is like 4.9, 4.99. But if you lose 5 from that, that's negative. So this is incredibly important that you know, as x approaches 5 from the left, the x minus 5 is approaching some negative number. It's approaching 0, definitely, but it's 0 from the left-hand side. So it's negative. That's the most important part. It's negative. So if it's negative, then those absolute value bars right there, you can remove them, but when you do, you're going to have to remove them like this. Because the absolute value is going to force that to be positive. Remember, that's just from this definition right here. If the argument of your absolute value is negative, and in this case we know it is, you can remove those absolute values, but it's going to be the opposite of the argument. So this is what I want, actually. I don't want the absolute value. I want this picture. All right, let's get it. So we're going to assume our function is less than a specific height. And remember, our function was this, 1 over x minus 5. And we're assuming already that's below some height. Well, I want to get x minus 5. You can see where I want to end up. So let's go ahead and take the reciprocal of both sides. It's x minus 5, therefore must be greater than 1 over n. So far, so good. And remember what I want. I want the opposite of that. So let me multiply both sides by a negative 1. And remember what happens when you multiply both sides of an inequality by a negative. The inequality sign switches. Now, you look at that and you say, this does not look right. This totally doesn't look right to me. Well, it is right, because that opposite, let me highlight it, of x minus 5 is a fancy way of writing the absolute value of x minus 5. So I'm going to go ahead and replace that. Notice I'm just kind of using this stuff right here to climb this ladder a little bit. And we're saying that has to be less than a negative 1 over n. Now, I need you to pay close attention to the signs of things. You should ask yourself, wait, I think there's something wrong. Isn't there something wrong here? You should ask that, because absolute values should never be less than a negative number. However, this right-hand side is not negative. It looks negative to you, but that's actually a negative 1 over a negative large number. So that should actually be positive. I'm not going to put greater than 0 because that's a weird inequality, but remember, n is super duper, I had to find it on my screen there, but n is super duper negative. So we have negative 1 over n, whoops, negative over negative, that's positive. So I definitely have the distance between x and 5 being bounded above or bounded by some positive number. And so that will be my choice for delta. You can see there are some slight considerations to take in when you're doing this, but actually once you kind of get used to it, it goes very quickly. So let's begin the proof. Ladies and gentlemen of the jury, I'm telling you right now, as x gets really close to 5 from the left-hand side, that function dips down to negative infinity. You guys all raise your arms up, say, no, it does not. I swear it doesn't. And I say, yeah, I'm telling you it really does. In fact, why don't you give me any negative number, as large as you want. And one of you is smart enough, you just say, no, I'm not going to. I'm going to say n. N is the negative number I'm going to give you. And you can just assume that is a hugely negative number. We'll change it when we want, but we're going to hand you some hugely negative number. I say, okay. Well then, for all hugely negative numbers that you hand me, I'm going to let delta equal negative 1 over that hugely negative number. And you also tell this jury, you know what? That number is positive. Delta is positive. Delta has to be positive, by the way, folks, because this statement right here, delta has to be positive. So somebody initially says, delta can't be negative, and you say it's not. It's a negative 1 over a negative number. It's positive. I say, oh, well, I guess you're right. Okay. All right. Well, thanks for interrupting me, but here I go. If it's the case that the distance between, and I should put 0 here. If it's the case that 0 is less than x minus, what are we approaching, 5? Great. If the distance between x and 5 is less than delta, I hope, ladies and gentlemen, you will all agree that this implies the distance between x and 5 is less than negative 1 over n, because that's my choice for delta. And they all say, yeah, sure, whatever, I believe you, okay. And you say, but ladies and gentlemen, if you note in my original claim here, x is approaching 5 from the left-hand side. And they say, yeah, well, we see that. And you say, well, since x is approaching 5, but from the left, the absolute value of x minus 5 can be traded out for the opposite of x minus 5. That, ladies and gentlemen, is just by definition of the absolute value. If the argument of the absolute value is negative, well, the absolute value wants to force it to be positive. So it's going to make it the opposite of that argument. They all say, yeah, I remember that from algebra. I say, you had good algebra teachers. So if that's the case, then you'll all agree, and I don't want to use then twice, it just sounds bad. I'll say therefore, because that's more mathy. Therefore, instead of the absolute value of x minus 5 being less than negative 1 over n, I'll say the opposite of x minus 5 must be less than negative 1 over n. And everybody says, yeah, okay. And I say, well, since you're all good with your algebra, I'm going to multiply both sides by a negative 1. You guys seem to be pretty okay with that. I say, yeah, great. And when I do that, I get to swap the inequality. And they say, yeah, that's okay. And you say, great, now I'm going to take the reciprocal of both sides because I want to end up, well, you don't tell them, but you know where you want to end up at the original function. So you say, now I'm going to take the reciprocal of both sides. They might say, why? And you say, I'm going to tell you in a moment. When you take the reciprocal of both sides, you guys all know that the inequality sign flips. And they say, yeah, of course. You say, ladies and gentlemen, I am done. And they say, quitter. And you say, no, I'm not a quitter. I'm done because I've just shown you that for that very negative number you've handed me right there, I have created a delta neighborhood so that your function drops below that very negative number. That is, as x gets really close to 5 from the left-hand side, no matter what negative number you hand me, you can hand me a negative number that's at this height right here. Let's just, for ease, say that's the negative number they handed me. I can create a delta neighborhood about x equals 5. And let me go ahead and do that here like this. Okay. I'm doing it on one side because that's all my argument states or stands on is a one-sided limit. But all those x values within that delta neighborhood will go below, their function values will be below that height of n. And so therefore I have proven to you that this will go to negative infinity because no matter what n you give me, I can land the function below it. And they say, amazing, this person's a genius. And you say, well, I'm just a hard worker. It doesn't take brains, it just takes hard work. Anyhow, that is an infinite limit at a finite point and a really messy screen. I super hate that. Hopefully in the next few days, my internet will be better. But anyhow, for now, that is the end of the precise definition of a limit. And that topic we are done with. However, just note, if you're watching this on YouTube and you know kind of there are other types of limit definitions, they just occur a little bit later. All right. Have a good day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.